We might as well get started. I just want to welcome everybody that is on this. I'm getting confused myself the way we started here, but anyway, everyone that was able to join us tonight, beautiful evening and everything. I usually make a couple announcements, but the announcement I'd like to make tonight is, Ellie, I'd like you to just share with people what's going on with the solar tour and what's happening there.
Sure. Solar tour, it's actually this year, it's called the MRES Sustainability Tour. It's a local chapter of the ACES National Solar Tour. We have been hosting it for at least 20, 30 years. I'm not even sure.
Yeah, 30 yeah.
Yeah, it's a tour of different solar homes across Minnesota. Any homeowner that's willing to open their doors, host an open house, and show off their solar systems and other sustainable features. That is happening this October 1st and 2nd, Saturday and Sunday from 10 to 4. It's up to each individual homeowner to determine their own hours, and we'll have those on our website too, so you can be sure that whatever home you want to visit is actually going to be available for the tour at that time. That'll all be on our website. So today is actually the last day to sign up. If any of you are interested in hosting your home on the site, deadline to sign up is today. And then after today, I'll have all the home information up on our website. So you all can peruse all the homes on the tour, October 1st and 2nd, check out all the solar sites, talk to the homeowners, learn about all their sustainable features, and just
Ellie,
yep.
Ellie, do we have like a percentage of hybrid and in person, or what's the count that way?
I think we have 9 or 10 in person, and then a few virtual as well, but most of the virtual just wanted to reuse their same videos from last year. So if you count those, I'm just gonna put all the last year's video and the 2020 videos on as well. So lots more videos to go through too if you're interested in just watching home tours, video tours that homeowners have put together in the past as well. Those will be on our website as well.
And just to add to what Ellie's saying is that the tour is going on nationwide with ACES. There's like 42 chapters of ACES across the U.S. And so, you can look at what we're doing here in Minnesota and what Ellie has put together. Or you can, check out what's going on in Texas. So really kind of an open deal to do that day. So anyway, try to check it out. It's really a fun thing. It's been lots of people. Last year, I think there was around almost 500,000 people across the country did it on that first Saturday of the month. So, well, anyway, moving on, I'd like to really share with you all what I think is probably one of the more exciting presentations we've had in a while. Dan was kind enough to agree to do this. Dan Ludwig is a senior engineer at Xcel working at Prairie Island on this hydrogen project. And he's going to share with us what is going on there and what the future might bring. So Dan, thank you so much for doing this, and welcome.
Great, thanks for the introduction. Yeah, so today, Dan Ludwig here to talk about making hydrogen from nuclear power. We're doing a pilot project at our Prairie Island nuclear generating plant. So today I'll give a little background on myself, talk about Xcel Energy and what our big picture goals are, and kind of how this project fits into that, and then I'll go into some details about the project. So Doug mentioned I'm an employee at Xcel Energy. Been there for about 9 years. I'm in our nuclear innovation group. And so our nuclear innovation group is all about bringing new technology to our nuclear plant, make it more efficient, and also find new use cases for nuclear power. And one of those is potentially using the power to make hydrogen. So I'm our lead in our research for nuclear power to hydrogen, sort of, all of the different things we're looking at for that. So just kind of walking through here, I'll talk about Xcel Energy in a broad sense here. So for those of you who aren't aware, we have based out of Minneapolis, as well as Colorado. We have dual offices, dual headquarters, and we've got 3.7 million customers, electric customers, and 2 million natural gas customers. So across the board, we're a pretty big company serving in 8 different states. And I think wind energy is the thing we're probably maybe most known for, but as well as other things, we're a nation leader in a lot of different things. And this all kind of points to, as we're looking forward, what can we do to help reduce emissions and help drive towards a more carbon-free system? So we've made 3 announcements recently. We were the first utility in the nation to make a carbon-free by 2050 electricity generation company. There have been a lot of other utilities that have done that, but we're the first one to do that. Since then, and with an intermediate goal of 80% carbon emissions from 2005 by 2030. Since then, we've also made 2 other announcements to be a net zero natural gas service by 2050 and have 0 carbon fuel for our customers' vehicles within 1 mile by 2050. So these are 3 very ambitious goals. And I'd say that the 2030 goals, we've got a pretty clear path to 2030, but that last from 2030 to 2050, there's going to take some new types of technologies that we probably aren't aware of yet, or that aren't fully commercialized yet, that we're going to have to develop to help us get there. And I'm going to be speaking mostly about this electricity goal here, but the other goals have a similar discussion. So just talking about that electricity goal for a little bit. Our plan right now to get to that carbon-free by 2050, we're going to be closing down our coal plants. We're closing a lot of megawatts of coal by 2030. We're going to be adding a ton of renewables to the system, 5,800 megawatts by 2034. We're going to be extending our nuclear plants. So like I said, I work on our nuclear side of the house. So this is part of what we're looking at is how can we keep the additional uses for the nuclear plants to keep them, extend them, to keep them extended and open for longer. And then this last one here, enable a carbon-free future, firm to special generation. We all love renewable power, but one of the challenges is, it's not always available. So in addition, when we take the renewables and the nuclear power, we're going to need some additional carbon-free dispatchable generation. And by that, I mean something that we can turn on when we need it. So when it's not windy and when it's not sunny, an additional source that we can turn on. Right now, we largely use natural gas plants for that. So if we want to be carbon-free and not use natural gas, we have to find an additional source. And that's where this hydrogen stuff starts to fit in. So, and we want to do all this in an affordable way and then keep the system reliable. We don't want to have rolling blackouts. We want to make sure people can afford their electricity and keep their power on. So that's kind of our big picture plan. And just looking at our kind of that, like I said, that 2030 plan, where we're going to reduce our carbon emissions by 80% from 2005 levels. You can see right now, we're about 60% carbon free in 2020, between nuclear, wind, solar, and then some other, largely, hydro and other generation. By 2030, our plan is to be 81% carbon free. And you can see again, we still have the nuclear, but we've got a lot more wind and a lot more solar that are coming on. Now, to get to that last, let's go one more slide here. You can see how our plan is to get this 80% reduction by 2030. We'll probably even get that by 2029. This red line, this IRP line, is what our plan is, our resource plan. So we're reducing our emissions over time, and you can see it will be getting down to that 80%, close to, even more than that, 85% reduction by 2030. This last slide here, kind of about our plan, shows a couple of slides that explain, what we're thinking about as we're reducing the coal and adding more wind. This left side is really interesting. It's a kind of a technical slide, but I'll try to explain it here. This red line is the total load that we have to serve. And so what that means, that's all of our customers, air conditioners and, refrigerators and all of that stuff, motors and pumps, everything that's running that uses electricity. Now, this blue line is if you subtract off all of the wind and all of the different renewables, you can see that this blue line is what's left that we need to make up for. Now, this orange box is our firm dispatchable. Think of that as our nuclear plants. that is something that's available all the time. And we've got a little box here for batteries, but you can still see that there's this little section of blue up here that isn't covered by our firm dispatchable load, isn't covered by our batteries, that we're going to have some sort of additional load that we can turn on when we need it. Now, across the bottom of this graph, I should have explained that. So across the left here, this is megawatts. So how big is the load? And this is hours. How many hours of the year? There's 8,760 hours in a year. So it's only for a few select hours that we anticipate that we're going to need additional power. But those few select hours are I'd say the important ones. It's peak summer when it's really hot out. Everyone's running their air conditioning. That's when we have peak loads. That's when we need to have that extra power available. So you can see our plan is really relying on renewables to reduce how much of that dispatchable power we need on a given day. And then also here, what this plan shows, our IRP, again, that's our resource plan, integrated resource plan. This is showing what we expect our average Minnesota residential bills to be versus the US. So the US average is this green line, and what we expect our bills to be. So trying to keep our customer bills low. So all that comes together with saying, we know that we want to get to carbon free by 2050. We've got a plan to get 80% of the way there by 2030, but the last 15 to 20% is really hard. You know, I realize now, I forgot to start out, if people have questions, Doug or Ellie, should we have them ask throughout the way, or is it better to wait to the very end? I can't remember what you guys said.
Whatever you're comfortable with, Dan. We often just have them, go to that little thing at the bottom and raise their hand.
Sure. Yeah. So that's great. So I'll stop right here. And if anybody has any questions on kind of the big picture Xcel Energy vision or strategy, go ahead and raise your hand, and we can go through that. I'll just kind of pause and chat while we're waiting, while people are thinking if they want to raise their hand. So like I said, that last 15 to 20% is kind of the part where we know we're going to need new technology. We know we're going to need something that's not available to us right now in a commercial way, because we can't, in the end, we wouldn't be able to add more renewables to get there, because when it's not windy, it just isn't windy. Okay, so I'm going to keep rolling. And if people have questions, just go ahead and raise your hand as we go, and I'll call on you and we'll go through.
I don't know how to raise my hand here. But
Yeah, I don't either.
Prairie.
Okay.
I saw that the battery line was level throughout. Why does that not increase in order to deal with your shortfall for when you need extra power during those hot summer days?
Right.
Yeah, and this is our plan that we've submitted to our regulator, the Public Utilities Commission, and we've proposed adding. This is quite a large battery, but it's small compared to the rest of the rest of the graph here. If we wanted to add enough batteries to cover this whole thing, that'd be a very, very expensive, prohibitively expensive project to put in.
But I don't know if you can hear me. I don't know how to raise my hand either. This is Chris Berta. My question was about the batteries also. We've been told over and over that we'll never achieve this without batteries. And so, energy storage in whatever capacity, whether it's batteries or another technique. But yeah, I agree. I'm wondering why this doesn't expand and contract, at different times. The battery.
Right.
Well, and in particular, these days, whenever you see a new solar field announced, it almost always is accompanied by some sort of a battery installation. I don't know about wind, but it certainly is the case with solar.
Sure, and I'm frankly not a battery expert, and I'm not really deep in that area, so I can't speak to it really in detail. I know batteries are really great for short duration storage. So for like less than 3 or 4 hours, that's where they're the most cost-effective energy storage mechanism. When you start talking about if you want to have extended power available storage for more than a couple hours, batteries get very expensive and very difficult to use in that capacity. So that's why we're talking about technologies that probably don't exist yet, And we're looking all across the board at various different energy storage means so that we can have that firm, dispatchable, all available power when we need it.
Yeah, you're right. I mean, again, when you hear about solar fields being announced and batteries being part of the installation, generally, yes, those batteries are really only meant to last about 4 hours. But there's two things. Number one, that can very often be enough to get you through a hump. In other words, it might be a 5:30 p.m. to 7 or 8 p.m. type hump, at the peak in the summer. But the other thing is that there's all sorts of other technologies to take advantage of batteries, such as virtual power plants and things like that. So, I mean, look, I don't want to beat a dead horse, just something to think about.
Yeah, and I appreciate the comment. Like I said, I'm an expert in hydrogen and in nuclear power plants. I'm not an expert necessarily in some of these other topics. So I appreciate the comment, and yeah, and I'll make sure we're thinking about it as we go forward. So yeah, so that's where, if you guys just want to jump in and start asking questions as we go, please feel free. So I'm going to keep rolling through here. So I think I've already said this, but we're looking at how do we get to that last 20%. So we're looking at, we need to evaluate and develop new technologies. We want to explore partnerships and reduce costs and bring things to market. We also want to invest in the new technology at the right time. And so all of these require us, and this all gets back to keeping customer bills low. We don't want to waste a bunch of money on technology that isn't going to be valuable and isn't going to get us to the end product. But at the same time, we need to be thinking forward so we can get there. And so the company as a whole is looking at a bunch of different things, be it carbon capture, advanced renewables, hydrogen, which I'll talk about in detail, advanced nuclear, advanced storage, so being batteries and other storage means. So we've got a whole group looking at just how do you get carbon free by 2050? So hydrogen is one of them. One of the cool things about hydrogen that I want to talk about is its many uses. So typically hydrogen is made through a process called steam methane reformation. And that's where you take natural gas, you put it through this process called steam methane reformation. It strips off the hydrogen and strips off the carbon. So when you make hydrogen, typically you've got a carbon dioxide profile that comes with that. Now you can also make hydrogen with electricity through the process of electrolysis, and that's what this graph is showing. So you can make electricity with renewables or nuclear or natural gas with carbon capture. And then you could use electrolysis to make hydrogen. If your electricity is carbon-free, then your hydrogen is carbon-free. So what we're looking at is, could we make carbon-free hydrogen and then use it for, and I'll talk about the uses in a minute here, and use it to help us get to our carbon-free by 2050 goals. So kind of as we've been talking about, one thing you can do with hydrogen is essentially like a battery. It's like energy storage. You can make the hydrogen, store it, and then later run it back through a gas turbine or a fuel cell up on the top here, and then make electricity. So in that way, it acts a lot like a battery, so energy storage. Another thing that we can use for hydrogen, this gets back to our natural gas goals. You could take hydrogen and blend it into the gas infrastructure. We're still exploring how much hydrogen you can actually blend in based off of the pipes and the appliances and how old things are and how much hydrogen those appliances and components can take. But you could blend hydrogen into the gas infrastructure to slowly decarbonize natural gas. Those two are kind of like, I'd say, part of our Xcel Energy utility bread and butter, right? That's what we are already doing, and that's ways we could decarbonize our system. Now, one of the beautiful things about hydrogen is that if you don't need to use it for one of these two cases, there's a bunch of other things you could use it for. Right now, over almost all of the hydrogen that's made is used either to make ammonia for fertilizer. Ammonia is just nitrogen out of the air plus hydrogen. And so that's fertilizer. And then chemical industrial processes, so think oil refining for that. That's where almost all of the hydrogen that's made today is used. And this, you think largely ammonia and a lot of this, you think down the Gulf Coast, you got a lot of hydrogen usage down there. But other ways that hydrogen could be used, transportation. We talk a lot, you maybe hear a lot about fuel cell vehicles, fuel cell trucks. One of the analogies I've heard is, battery electric vehicles are great, but anywhere you've got a diesel engine, that'll probably end up being a fuel cell vehicle at some point, just because having a battery that big for that big of a capacity would be a challenge. So that'd be one potential use. Synthetic fuels. This is a cool one. If you take CO2 from a carbon neutral source, like from an ethanol plant where the CO2 came from corn, essentially, came from the atmosphere, and then combine it with hydrogen, you can synthesize pretty much any hydrocarbon, such as a jet fuel or a diesel or gasoline for your car. So if anyone's seen some of the announcements, some of the major airlines now are using it. Sorry, I got some feedback there. Could somebody go on mute? Sorry, I'm getting a lot of feedback. Some of the major airlines are now using what's called sustainable aviation fuel, where they take hydrogen made from a carbon-free power source and combine it with CO2 from a carbon neutral source. And they can now put that back into an airplane and reduce the emissions from their airplanes. So it's another great use for hydrogen. I already talked, I'm just gonna kind of skip around, and another last one I'll just talk about real quick is steel production. You can use hydrogen in the steel production you can use a different process to make steel and really decarbonize how steel is made. So there's a lot of industries that can use hydrogen in addition to the traditional utility industry. So that's one of the reasons why hydrogen is such a high value commodity in our mind. So why aren't we doing this already? Well, hydrogen is not cost effective. Just trying to make a little bit of a comparison here. Could hydrogen follow the same cost curve as wind? Wind back 20, 30 years ago, 40 years ago was not cost competitive. But as demand went up and we built more windmills, there was more manufacturing, there's more supply, more demand, costs came down. And that's really when you saw, starting in 2000, I'd say, is really when you started to see a lot more windmills going up as the cost came down. And so we're looking at hydrogen similarly. How far back are we on that cost curve? I'm getting some feedback again. If someone could go on mute, thank you. So this is just some various predictions for what the cost of hydrogen will be going out 2020, 2030, 2050. These are all various public companies. Maybe you'll recognize some of these acronyms, like the Department of Energy, the DOE, the McKinsey. They're a big consulting company. Everyone's got projections. I wouldn't put my stock in any single one projection, but what you can see is a general trend. Everyone expects hydrogen prices right now are pretty expensive. I should say they're comparing to the hydrogen made from steam methane reformation, which is this gray line down here, which is pegged about $1.50. That's assuming some gas prices like at $3 to $4 per MMBTU, which if you're following natural gas prices, they're a bit higher right now because of, as you can see at the pump, it's a similar story with inflation as well as the Russia-Ukraine war going on. There's a lot going on that affect gas prices. So that's a bit higher right now. But just kind of pegging this at that long-term average, it's about $1.50 for hydrogen per kilogram right now. So we're in this for the long haul. We're doing research now. We're looking at things now. We're looking forward to say by 2030, this 2030 to 2050, when we're trying to get that last 10 to 15 to 20% of our carbon-free generation, is that when hydrogen will really start becoming cost competitive. And the key drivers there really are the infrastructure. The manufacturing and the infrastructure need to be built out for hydrogen. So what are we doing about hydrogen? And I'll just pause for a second. If anybody has any questions, that's kind of the background educational side. Anybody have any questions about that? So, and I'm going to talk specifically about Xcel Energy nuclear. Xcel Energy non-nuclear is also doing a bunch of work on hydrogen. I can kind of speak to that broadly too, if anyone has questions on that. but I'm going to talk specifically what we're doing in nuclear. So we formed a consortium with 2 other utilities, Energy Harbor, based out of Ohio, and Arizona Public Service, based out of Arizona, as well as Idaho National Lab up in Idaho Falls. We all have nuclear power plants, and we're all exploring how could we integrate nuclear power with hydrogen. There's a couple of terms here I'll take a few minutes to explain because it's important to show some differences here. But Energy Harbor is leading, we're doing this in a multi-phase approach. Energy Harbor took phase 1, and they're installing a low temperature electrolysis skid, like 1 to 2 megawatts. So it's a pretty small scale, low temperature electrolysis system, and they're doing it at their Davis-Besse plant in Ohio. We also, as part of phase 1, Xcel Energy and APS did what's called a technical and economic assessment. What this did was, this was work completed by Idaho National Lab, Argonne National Lab, and NREL, National Renewable Energy Lab. We worked together with them to evaluate what were some potential options where we could model making hydrogen from the nuclear plant. We got a lot of really good insights from that. Now, with anything, any sort of a government research report like that, you know, it's pretty high level, but it has a lot of great pointers to let us know you need to have this sort of cost structure, you need to have this sort of operating profile to make it an economic case. So we had that big term, and that was looking at what if you took an entire nuclear plant dedicated to make hydrogen. So it's a really big picture. Then in phase 2, Xcel Energy, we're taking the lead, and we're doing what's called a high temperature steam electrolysis demonstration. So I just want to point out here the difference between low temperature and high temperature. I'll explain that more in a bit, but that's really important. On the next slide, I'll explain kind of how the high temperature system works. But the thing a couple of comments I want to make about that is that the high temperature system is expected to be 30% more efficient than the low temperature system. And so this high temperature system it's expected to be 30% more efficient. And that means you can use 30% less electricity per kilogram of hydrogen that you make. Now, when you look at the cost of hydrogen that's made through electrolysis, made from electricity, about 70% of the cost of hydrogen is the cost of that input electricity. So if you can reduce the amount of electricity you use to make the hydrogen by 30%, let's say, you could reduce the total cost of the hydrogen by like 20%, which would be huge. The caveat with all this is that this high temperature electrolysis, the technology for that isn't nearly as developed as a low temperature electrolysis. Low temperature electrolysis has been around for over 100 years. There are some installations that have been going for a long time. It's getting a lot more attention now and really scaling up. So for example, you could go, I'm not going to say to the store, but you can go out to specific vendors and you can buy up to a 20 megawatt, like 15 to 20 megawatt low temperature electrolysis system. For high temperature, you can't even buy a 1 megawatt system yet. There have been some announcements, maybe up to 10 megawatts that have just breaking news, but in general, the technology is for high temperature is much more lagging than low temperature. So that's why we've decided to focus our research on this high temperature electrolysis, because it is more efficient and it's actually got a lot of room to grow. If you think of that cost curve, because it's still a nascent technology, still developing, there's a lot of potential for the cost to come down yet. Also under phase 2, Arizona Public Service has some DOE funds. They're doing design for what's called a reversible high temperature electrolysis skid. And this is a cool idea in that an electrolyzer and a fuel cell are essentially the same piece of equipment running forward or reverse. An electrolyzer takes water and electricity and makes hydrogen. A fuel cell takes, make sure I say this right, takes hydrogen and makes electricity and water. And so they're just doing design, engineering design. So they're not actually installing anything, but they're looking at, could they install a system that when power prices are low, when you've got peak solar out in Arizona, could you use low, cheap power that you don't really need and make hydrogen? And then in the evening, when your solar isn't making as much power because the sun's going down, but now everyone's running their air conditioning and we have peak load, could you then turn that same system around, stop making hydrogen, use this hydrogen you stored up and run it through the system and make electricity? That's a really cool system that they're evaluating. So that's phase 2. The third phase is led by Arizona Public Service. And they're looking at a large scale, low temperature electrolysis system, like 20 megawatts. They're looking at, and specifically what they're looking at is mixing hydrogen into a gas turbine to help decarbonize their natural gas infrastructure. So they would mix the hydrogen with the natural gas, burn in a turbine and make electricity at a lower carbon intensity than a traditional turbine. They're also looking at doing a syngas pilot where they'd make that synthetic fuel, be it jet fuel or synthetic diesel or whatever. And then we're all working together to look at, phase 4. And there's been a lot of laws, a lot of funding passed from the government, from the Infrastructure Investment and Jobs Act, or that bipartisan infrastructure bill, if you remember that from November of last year. There's I think $9.5 billion for hydrogen in that bill. So that's been spurring a lot of different discussions about what's next for this consortium. How can we plug in to do future work? And I'll just pause there for a minute if anybody has any questions.
Hey, Dan, question I've got is this, Doug. What's happening around the world? Are we doing something unique, or are other countries doing this already?
It's a great question. Thanks for that's almost like a plant. I should have, something I forgot to mention. So this high temperature electrolysis kit, this will be a first in the world type application. Pairing high temperature electrolysis with nuclear has never been done before. There's people all over the world watching us. I was at a virtual conference in Vienna over Thanksgiving, actually, talking to the International Atomic Energy Agency about all the nuclear plants in the world are wondering, how are we doing this? What are we thinking about? How are we going to get there? Across the world, other nuclear plants are looking at low temperature electrolysis. And across the United States, there's another nuclear power plant, 9 Mile Point, owned by Constellation now. They're also doing a low temperature electrolysis system. So this is definitely something that's taking off. As far as non-nuclear, there's a bunch of hydrogen projects going on tied with renewables. You think down in Florida, I think there's a big one where they're tying solar to solar to hydrogen. There's some down in the Gulf by Texas that they're talking about. And I think Spain and Finland each have announced very large hydrogen projects tied with renewable power. So yeah, so there's a lot of work going on in hydrogen right now across the world. A lot of governments are putting a lot of money towards it, and a lot of big companies are sinking in to really jump on this one.
Is the military involved in this at some level, I would guess?
I can't speak to that one for sure. I haven't heard of anything, but that doesn't mean that they're not. I know that I think I've heard of various military decarbonization goals, and if you want to decarbonize like ships, it's really hard to replace diesel bunker fuel. And so some of those synthetic fuels, or even ammonia made from carbon-free hydrogen, could be a replacement to decarbonize large ships. But then even like large vehicles, if you want to put a fuel cell in. So yeah, I know there is some DOE work, or DOD work, but I can't really speak to that.
I also know there's major projects going on out at University of Minnesota Morris, where they're doing hydrogen and ammonia and powering vehicles and using it for fertilizer. Is Xcel, talking to them at all, or is
yeah? So Xcel is actually one of the sponsors of that project. Yeah, and so yeah, Mike Reese, I talk to him pretty regularly. He is the lead of that project out there. He does a great job. Yeah, they're doing wind to ammonia, and like I said, ammonia. They see hydrogen's great in all the things that it can do, but one of the drawbacks with hydrogen is that it can be expensive to store and move, whereas ammonia is very cheap to store and move. So if you convert the hydrogen to ammonia, then you can store it and move it easier. Now, then you can take that ammonia and could you put it into a tractor? So they have tractors running on ammonia as their fuel. Or you could burn ammonia in a turbine as well. There's some challenges with that relative to NOx, so nitrogen oxide emissions. But there are things that they're looking at to try to figure out. So yeah, Mike, they're doing great work up at the University of Minnesota Morris, and they're really paving the way for some of those critical end uses of the hydrogen.
Yeah, I was in a meeting where Mike was talking about some of the huge storage tanks that are out in that part of the state where ammonia can be stored, you know, and so talk about storing it for energy purposes too, you know.
Yep.
Yeah. Okay. Thank you.
Yeah, you want to be really careful about storing ammonia near populations, though.
Yeah. Yep. There's definitely some safety
if there are
concerns.
leaks. Yeah. Bhopal, India, 2,500 people dead.
Yep. And I just realized I didn't have my laser pointer on. I had a pen on the whole time. So I've been pointing to things on the screen and you haven't been able to see it. So I'm really sorry if you've been lost on some of the slides I was pointing at. So we'll keep going though. So this is a technical schematic of how our hydrogen system will connect to our nuclear plant. So on the top side here, we've got the nuclear plant. And the bottom side down here, we've got our hydrogen plant. So I'm going to explain the nuclear plant first, then I'll explain the integration of the hydrogen plant. So for those of you that have experience with power generation, this may all be things you know, but the way that we make nuclear power is we've got at Prairie Island at a pressurized water reactor, there's two loops. One loop over here, which is called the primary loop, where we have water that pumps into the reactor. It goes through a big heat exchanger called a steam generator, and then goes back to the reactor. So that's a closed loop of heating and cooling water. Then we have a second loop where we take water, we call it the secondary. We take water, cold water, we pump it in that steam generator, it boils, turns to steam, it turns a turbine generator and makes electricity. After it turns the turbine generator, it goes back down to the condenser and back through the cycle again. So that's another closed cycle. And then we've got a third cycle where we take cold water, either from the river, but from the Mississippi River for both of our nuclear plants. We take it from the river and we go through here, we cool off the water in our secondary, and then we send it back to the river. We use cooling towers in the summertime to help cool off that water before we return it to the river, but then we return it to the river just a little bit warmer than we took it out. And we have a permit that allows us to return the water at a certain temperature to make sure that we're not negatively impacting the river. So that's at a super high level how a nuclear power plant works. It's very similar to a gas plant or a coal plant, other than this part about the nuclear reactor. Now, to make hydrogen through electrolysis, we have this unit in the middle here we're calling our steam electrolysis unit. We're taking electricity made by the nuclear power plant and sending that to the electrolysis unit. And if you can remember back to your high school chemistry, if you took chemistry way back when, it's pretty simple. You have the way electrolysis works in very basic terms is you've got a positive and a negative side in water. You'll apply that voltage potential across them. You've got some sort of membrane to split that you help drive the positive and negative ions different directions, and you can separate the hydrogen and oxygen. That's a very basic explanation, but that's basically what we're doing with the electrolysis unit. Now, in low temperature electrolysis, you just apply cold water or room temperature water to the electrolysis unit. It splits it into hydrogen and oxygen. What we're doing in high temperature electrolysis is we're taking some of the steam made from the nuclear plant and bring it down here to a heat exchanger. And what we're doing is we're actually going to boil the water that goes into the electrolyzer. The steam from the nuclear plant will go through the heat exchanger, it'll condense, it'll go back into the nuclear plant. So again, that's a closed loop. We're keeping the entire nuclear plant cycle to itself. But then we have this I'd say, fourth loop down here now, where we have water being boiled, going to electrolyzer. And by using this steam from the plant to boil the water going into the electrolyzer, we reduce the amount of electricity needed to split the water into hydrogen and oxygen by about 30%. And like I said, that can be a game changer when you start thinking about large-scale hydrogen integration. Now, this system we're doing is a pilot. It's really a proof of concept, very small scale, just to prove we can do it. The key value isn't the hydrogen that we're making. The key value is the lessons learned as we figure out how to pull steam and electricity out of the nuclear plant to make hydrogen. In general, nuclear power plants are made to make electricity. We don't do anything else. We do it really well. Our Xcel's nuclear plants have been running just amazingly. And we making electricity around the carbon-free electricity around the clock. So this will be something new. And so working through all the nuclear power plant processes and regulations, and then working with the Nuclear Regulatory Commission. So there's, as you may be aware, nuclear power plants are very heavily regulated. We have many regulations that to comply with. All sorts of different safety systems and safety requirements that we're going to validate as we go through this. So what we're doing on a very small scale is setting us up for the future in a large scale. What can we learn now so that when we want to do a larger scale, we can do that more efficiently and faster. Another key aspect of this project, like I said, was the high temperature electrolysis industry, especially the domestic high temperature electrolysis industry, is not nearly as developed as a low temperature electrolysis industry. So one of the DOE goals is to help develop the domestic high temperature electrolysis industry. So by selecting a domestic manufacturer of our electrolysis system, we're helping essentially make that pull, that industry, or that, you know, kind of that economy-wide pull for them to start scaling up. So they can look and say, hey, there's a potential for our electrolysis units to be used in nuclear plants. Let's build a bigger factory so we can make more of them. And as their factories and economies of scale increase, they get more experience, they get better supply chains, everything, the costs will come down. That's really a win-win for us as we watch that industry develop. So I'm just going to stop here for a second. If anybody has any questions on this graphic, I know if you're not used to power generation discussion, this graphic can be kind of a lot to look at.
Dan, after a project like this, will Xcel and the companies involved like patent this process, or is it wide open? Or
being that it's DOE funded, we'll be sharing our lessons learned with the DOE and with the rest of the world, the rest of the country, I guess. So there are some aspects that could potentially be patented, but we didn't really see the value in that. We really see the value in helping get other people to also do this sort of similar project, because the more pull there is of other nuclear plants trying to do the same thing, that'll help bring costs down. So we don't plan to patent anything out of this project right now, but that's a good question. Thanks, Doug. Okay, so I mentioned that this is a very small scale project. So there's a little number on here, 90 kilograms a day of hydrogen. A typical large scale hydrogen production facility using steam methane reformation is in the order of like tens to hundreds of tons of hydrogen a day. So a ton is 1,000 kilograms. So I know we're using metric system numbers here. That's the whole industry uses metric system numbers. So this is very small scale. So if we wanted to, you know, do something great with this hydrogen, it'd be limited. And this next slide really talks about that. So how much power are we using, for example? Prairie Island, between the two nuclear power plants, powers about 1 million homes. How much electricity are we using for our pilot? Enough to power about 150 homes. So it's really not a lot of power. It's very small scale. And we're doing that on purpose because of one is the availability of the electrolysis system, but two, also we want to do this small scale to work through all the regulations when it's smaller in scale. And just an example of what could you do if you had 90 kilograms of hydrogen a day? If you had a hydrogen fuel cell electric vehicle And if you drive out to California, they have fueling stations and they have hydrogen fuel cell vehicles. Typically have a tank of about 5 kilograms when filled, and they can take about 300 miles, drive about 300 miles on a tank. You could fill that tank about 18 times, let's say, with that 90 kilograms a day, 18 times a day. You could drive about 5,400 miles. So if you think about it that way, as a personal user, driving 5,000 miles, that's a lot of miles. But when you think about large industrial facility, large industrial usages, or even like a fuel cell filling station, if only 18 cars could fill up in a day, it's really not that much hydrogen. So just to make the point, we're doing this small scale hydrogen project so that we can learn the lessons from the regulatory process, things like that are related to the scale, but you can also apply them to the larger scale system. The next slide here, I've got this is a schedule of the project here. We were notified of the award from the Department of Energy on October 8th of 2020. For those of you who know your periodic table, the atomic mass of hydrogen is 1.008. And so the US Senate has declared a resolution that October 8th, 10:08 is Hydrogen Day. So if you want to have a party for hydrogen, have it on October 8th. Also, if you're looking for announcements from the Department of Energy, they tend to be on October 8th or thereabouts. So if you're ever wondering what's new with the US Department of Energy and hydrogen, keep your eyes out around the first week of October. So we're all looking forward to a month from now, what's coming next. There's some big announcements that we expect to be coming, and we're thinking they'll probably come October 8th. So we were notified of the award on October 8th. It took us until June 1st of 2022, so almost a year and a half, over a year and a half, before we actually had the funding available to start the project. Part of that is working with the federal government. There's a lot of red tape, a lot of processes, a lot of things you have to comply with. And Xcel, we typically don't do research and development. This is a new area for us. We typically, make power for our customers at an affordable price, and make sure it's reliable. So doing research, looking forward to 2050, this is a new thing. So it took us a while to get all of our processes lined up with what's required from the government. And also just make sure we could execute the project on schedule and budget. So we started on June 1st, and roughly how the project will go, we're doing engineering right now. We expect all of our engineering to be complete by first quarter of 2023. At that point, the electrolyzer will be built, and it'll be shipped, and it'll show up at Prairie Island around the fourth quarter of 2023. At that point, we'll install the electrolyzer. It'll take a couple of months to get installed, kind of third quarter, first quarter of 2023. And then by 2024, we'll have the system installed and up and running. This project, being a demonstration project, we're going to be running the system. Initially, we'll be taking it kind of through its paces, but then we'll have it up and running steady state in that second quarter of 2024. I've got a very sad baby. I don't know if you can hear that, Doug, or not, but I've got a sad baby crying outside. I've got an 11-month-old that wants to visit.
Yeah, I can barely hear him.
Okay, yeah, that's him. He's a sweet little boy. All right, well, that's my last slide, Doug. I do have a final slide, required acknowledgements and disclaimers. Just so you know, this was funded by the Department of Energy. I've mentioned that several times. So we got a $14 million grant from the Department of Energy. It's an 80-20 cost share, so the federal government pays 80%, Xcel Energy pays 20%, and they're really pushing to help this hydrogen industry develop. And then you can read this long thing on your own. It essentially says the government paid for this, but they are not saying that this is right. They're saying it's on us to make sure it's right. So with that, that's my last slide, I think. I'll open up for questions if anybody has any.
I'll jump with the first one. Dan, one thing I've heard is that in the automotive side, one of the biggest uses appears to be, in fact, I have a friend working in a company in Arizona where they're doing over-the-road tractor trucks, 18-wheelers, and powering them with hydrogen. Are you aware of any of that?
Oh yeah, there's a lot of movement in there. There's several big companies that are they would like to be the hydrogen producer. They want to put down the fueling stations. They want to essentially dot the highway, the interstate highway system with refueling, with hydrogen fueling stations. And so yeah, that could be a very, very real potential use of hydrogen. And like I said, if you want to decarbonize trucking, it's really hard to do with a battery on the truck. It takes up so much space and it takes up so much weight. And so yeah, so there's several big companies across the country who are really, I'd say maybe startups, but they're really starting to get a lot of money, be it from venture capital or whatever, to start looking at, well, buses are another one. So buses would be another thing. It's hard to put a battery on a bus and, you know, still make it economic. So big trucks, buses, anything that's, you know, got a big diesel in it. Yeah, there's definitely a lot of interest in that.
Dan, did you say that that Xcel expects to be out of coal by 2030?
Yeah, that was way back at the beginning. Let me show you what that one looks like. And this was referencing, I believe, our Minnesota resource plan.
Oh, okay. So that's Minnesota only. It's not necessarily company-wide.
You know, I'd have to validate that question and get back to you.
Well, it actually doesn't really matter. My point is that what I wanted to point out is that yesterday the Department of Energy released a study saying that 80% of U.S. coal power plants sites could be converted to nuclear power plant sites if they use those this new generation small nuclear plants. And if the industry follows through on that, what it means is that nuclear isn't going anywhere, and that just kind of underscores the direction that you're headed. Is that nuclear may be around for longer than people may have expected, and if that's the case, then you know, if there can be a side benefit for hydrogen as well, then all the better.
Yeah, I'm familiar with that report the Department of Energy published. Yeah, and it's when you look at a coal plant, if you take down the coal plant, if you keep that switch yard there, running transmission lines is really hard. But if you already have the switch yard and transmission lines, and they probably already have a cooling water source, there's a lot of infrastructure there that, yeah, you could put down a new nuclear plant. And yeah, I think a lot of people are recognizing now that in a carbon-free world, we can't 100% renewables. It's unfortunately not going to get us there. We need to have the buzzwords we use are firm and dispatchable generation, something that you can turn on and turn off when you want it, and you can know that it's going to be there. And so, yeah, that we're looking at, and Xcel is looking at, you know, advanced nuclear. I think I had a slide that kind of talked about all the different things we're looking at. And yeah, and we're not ruling anything out for how we get to that carbon free by 2050. So yeah, great comment.
So in the chat, there are a couple questions, and one of them is mine. And of course, the elephant in the room is what about nuclear storage and nuclear security? And what are you doing about that? I'm not a nuclear fan, so you know I'm listening to this because I realize the reality of some of this. But you know, what other kind of nuclear plant is out there that's going to be less dangerous? And anyway, that story. What have you?
Sure. Yeah, and I can speak to that at a high level. Yeah, if you talk about current nuclear plants versus future nuclear plants, the future nuclear plants are a lot of the buzzword there is what they call passive safety systems. So if you remember the Fukushima nuclear reactor that melted down in Japan, the problem they had wasn't the earthquake, it was the tsunami. And the tsunami didn't affect the nuclear plant, but what it did is it wiped out their diesel fuel. And they got their diesel generators all wet. So once they lost power, because the tsunami also knocked out the switch yard, they would have normally relied on their diesel generators to run pumps to cool the reactor, which would have worked fine. But their diesel fuel got all wet and wasn't able to be used. And so that's the way our plants work, right? If there's ever some sort of situation where we can't make power and cool our reactors or take power from the offsite, we have dedicated pumps and diesel generators to cool the reactor. The advanced reactors are all designed such that they're called passive safety. You don't need those pumps. You don't need those generators. So yeah, so that really reduces the risk of a nuclear meltdown. As far as that answers the question. I think there's another question about waste storage. Yeah, waste storage, that's another big one. So right now, all of the fuel, like at Prairie Island, all of the nuclear fuel that's ever come out of the reactor is stored on site on a big pad in these big concrete bunkers, and it's sitting there. The Department of Energy passed a law back in the 1980s saying they'll take it and put it in a depository. We're still, and that's been back and forth. And if you're familiar with Yucca Mountain, I don't think that's ever going to happen. But we have a plan to store that, and the Department of Energy is willing to take it. Now we're actively looking at if in absence of the federal government taking the fuel, is there some other way that the private industry could take care of it? So we're exploring that. There's lots of discussions there. You know, what could the future hold there? But you know, if you think about any sort of power generation, you think of like coal or gas. How much of their byproduct goes out the top of the stack. All of our byproduct is held, on one pad. It's the size of a football field, approximately. So that's where all of our stored fuel, our used fuel is.
In the river. Right, it's surrounded by the Mississippi River, right? The pads?
The pad's
Yeah.
on site at the nuclear power plant. Yep.
Yeah.
Yeah, the classic solution to that I think the science fiction writers like is to just take all that stuff and blast it into the sun.
Yeah, yeah, that's a good one. I've also heard sink it to the bottom of the ocean. Yeah, neither of those are real good ones. Other countries reprocess their fuel, and they can reduce all of the amount of reduce the volume of their radioactive material by over like 90-95%. That's currently not an economic option right now, but as we're looking for that carbon-free by 2050, there are a lot of things that aren't economic right now that may become economic as people start putting more effort into that. So that's another opportunity that we're talking about now to see what can we do with this spent fuel, because there is a lot of value. You can make a lot more power out of that spent fuel if you could reprocess it.
Right. Dan, there's several questions in the chat. Could you address those?
Yeah, I just saw it here, so I'll go ahead and just walk through those. So the first one from Tommy: what steps are going to be used to expand the hydrogen production and hydrogen batteries? Tommy, could you just speak to that a little more? I'm not sure exactly what you're asking. I don't know if we lost Tommy. So I guess the next steps to expand would be to do a larger system. So we need to buy a larger system, send more power to it, send more steam to it, but that would be how you expand it. What part of the temperature of the process makes it hot? So that's sending that steam. So you're sending steam to the electrolysis unit instead of cold water. So that's why it makes it high temperature. The electrolyzer itself operates very hot. So you send in steam that's around 300 F, and the electrolyzer itself actually heats that steam up even higher, up to like 15 or 1600 degrees Fahrenheit. Very hot. And that system operates very high, so you get a high efficiency. James, sorry, but I'm a Debbie Downer. I see right in Europe's biggest nuclear plant is being used as a political pawn. What consideration is being paid to terrorist threats to nuclear power? So great question. We have a great security force with a very impressive security plan. We have one of the largest forces in the state of Minnesota is at each of our nuclear plants. And so it's definitely something top of mind. It's something we're always thinking about. It's getting into the nuclear plant. Every time I go in, it's going through security. So yeah, security is definitely something that we're considering, and we have something built into our plant design.
I mean, I'm
Um,
like a missile, like a missile attack. I think that's what, and both transport over ground, and also, any materials, and then also missile strikes.
Sure. So, so our reactors have containment buildings around them, so the big concrete domes, and so those have been designed. I mean, the initial design way back in the day was a tornado throwing either a telephone pole, so like 6 inches long by 6 inches diameter, or 12-inch diameter by 20 feet long, whatever telephone pole is, or a VW bug. And it said both of these things, one is a very small but very high energy hit, and one is a big but a larger mass hit, and you have to withstand those. As far as, launching missiles at our nuclear power plants, that's something that if we're in that situation, it'd be a little different than what we've been kind of designed for. As far as something coming along the ground, we have physical things that would stop someone from driving a truck or some sort of something. We have, physical things that you can't just get through. So that would stop you from getting to the nuclear plant. I see another question here is from Barbara. Is the hydrogen generation process amenable to using nuclear energy only when it's available? That's a great question. So the hydrogen system can be ramped up and down. So one of the things, I should have mentioned this earlier, one of the things that we're talking about with nuclear power is that, I'm going to go back to this slide. This picture here that we talked about, and I realized I didn't have my pointer on at the time, sorry about that. But when we have a lot of wind available, so when we have our max wind load that's dropping our need for power, instead of having the nuclear plant make power, we could use it to make hydrogen. Whereas when we don't have any wind and we're actually operating way at this red line up here, then we would use the nuclear plant to make electricity. And so the hydrogen plant can be ramped very quickly to follow the wind generation. So yeah, that's one of the other key benefits. I should have mentioned earlier, sorry, that the hydrogen system and then really allows the nuclear plant to mesh well as we build up more and more renewables. So it really makes the nuclear plant more flexible to work with, to play well in the sandbox with others. I think that's the last question I see. Oh.
Years ago, Dan, Xcel or NSP used to always say they could not ramp up and down nuclear plants, and that has changed now, right?
That's correct. So we call, the buzzword we use is called flexible operations or flexible generation. Right now, we operate in what's called a day-ahead market. And so the grid operator looks at how much power we're going to need for the next day and says, Xcel, we're not going to need your nuclear plant tonight. Can you back off by 20%? And so we'll actually back off our nuclear plants by 20%. So you're right. We used to be full on 100% all the time. And now we are backing off by up to, I think, 20% at our 20 or 25% at our nuclear plants when needed, when we have too much power on the grid. If it's a windy day, I remember back in April of 2020, when the whole world shut down, we were flexing or turning down our nuclear plants almost every day, every night, because there just wasn't that much power demand. And it was windy because it was spring, which, spring tends to be spring and fall tend to be the windiest time. So we definitely have that power. The thing about flexing is great. It allows more renewables on the system. But with the nuclear plant, that doesn't actually save you anything because we refuel our reactors. It's right around every 2 years, no matter how much power we make. So it's, if we run it 100% all the time and use all of the energy from the reactor, or if we flex every day and every other day, let's say, and only use half the power from the reactor, we're still going to refuel every 2 years. We have to shut down the reactor and do a bunch of tests and maintenance, and we'll replace the fuel. So if we want to get the max energy content out, what making hydrogen does is it allows us to use the maximum amount of fuel, keep the reactor at full power, which the reactor wants to operate at full power. It can operate at lower power, so it wants to operate at full power. and allows us to just divert power to make hydrogen or make electricity. Barbara, I see that you have your hand up. Would you like to ask a question?
No, I'm sorry. I did want you. I appreciate you answering those questions.
Okay.
Dan, we did get one more question. Chris was asking about the situation in the Ukraine. Any thoughts there?
All right. Can I caveat this with I am not a Ukraine expert, but what I can tell you what I've read in the news. So if I say anything, I would encourage you to also read the news and see what you see what you read. So the last I heard, the big deal is if they don't. Whenever you hear that they were disconnected from the power grid, that's big. That's kind of the big deal. Like I said, those reactors are very similar to like our Prairie Island pressurized water reactor, I believe. Similar in that they need power to run pumps to cool the reactor. Even after you shut down the reactor, you still need to cool the reactor because the reactor is still radioactive and it's still actually giving off some heat because of the radiation. And so what they did a while back, they shut down, there's 6 reactors there. They shut down 5 of them, and they had 1 reactor supplying power to the other 5 reactors, as well as its own power, to make sure that it could keep all of the reactor cores cool. And that's when they were on that, if you read, they were like on nuclear island or in island mode or something where they're disconnected from the grid. And so that means they couldn't get power from another power plant to power their cooling pumps. They do have backup diesel generators on site so that if they did have all 6 plants shut down, weren't making any power, they could use those diesel generators to make power on site and make electricity to run those cooling pumps to keep the cores cool. They're a little leery about going onto their diesels because they're afraid that the war would prevent them. They have about 10 days worth of diesel fuel on site. They're a little leery about using the diesels because they don't want to run out, because within 10 days, could they get more diesels? And so right now, they have all 6 reactors shut down, I believe, and they're connected to the electricity grid. The electricity grid is what's supplying power to all the reactors to cool the cores, to power the pumps to cool the cores. And Barbara, I see, are the Ukrainian reactors shut down? Are they using up the fuel normally? So when you're shut down, you're not using the fuel at all. There's very, very little, there's no, uranium isn't being fissioned, isn't making energy. So there's no additional nuclear reaction going on. It is still hot, and it'll stay hot for a while as the radiation decays off. But so that's the high level of what's going on in Ukraine right now. You know, that's what the status of the reactors are. You can also talk about, you know, where the Russians are, who's working. The Ukrainians are working, the Russians are occupying. You hear terrible stories of the Russians, you know, kind of being guards at the plants. So yeah, it's a very bad situation. And really the International Atomic Energy Agency, which is a branch of the UN, just released a statement saying Russia has to leave the plant now. Like that's like straight up, you know, saying Russia, you need to leave the plant alone. So hopefully that happens soon.
Hey Dan, one final question. With this project that you're working on, based on everything you know at this point, do you feel that Xcel will go forward with you know a bigger system, or is that too far in the future to say?
Yeah, I can't speak with any real certainty there. You know, we're still making those plans, but I can tell you that it's top of mind for a lot of people in the company that are focusing on this. Is how can we turn this research, this pilot plant, into a big what's next? And then, so like I said, we talked a lot about what's going on in nuclear. In the rest of the corporation, I think I alluded to this earlier, I can just say at a high level, we're looking at how can we make hydrogen from renewables using that low temperature electrolysis? How can we blend it into gas turbines? How can we blend it into our gas infrastructure? All those sorts of things. So, you know, without putting any numbers or dates on, Xcel is definitely moving this direction. And, you know, I'd say keep your eyes open for press releases and stuff like that as Xcel starts really starts really getting into the hydrogen industry.
Yeah. Well, we thank you so much. This has been a great presentation. You shared so many interesting things, and I think some of us knew a little bit about it, but this helped so much to understand what's happening, and even a little bit more about how the plants operate and everything. So we thank you so much for doing this, and we're gonna have Ellie shut us down here in a few minutes because we've got another meeting coming up right behind this, and so I'll talk to you probably tomorrow. Okay.
All right, very good. And Barbara, I see your question about selling hydrogen for transportation. That's definitely in the considerations. Like I said, kind of back to that wheel, we're looking at the whole wheel. So what's going to make the most sense for Xcel Energy? So it's definitely in consideration. Doug, really thank you for giving me the opportunity to come talk to the crowd. If you have any questions, anything that I didn't get a chance to answer, something that you wanted to follow up on, send a note to Doug and he can get in contact. He's got my contact information. But happy to talk more about any of your questions. And thank you very much for the time.
Thank you very much.
Have a great evening.
Thank you, Dan.
Have a great night, everybody.